Good afternoon to one and all. Before we start the session, I request all participants to please remain muted and keep the cameras turned off to ensure a smooth and uninterrupted program. It gives me immense pleasure to welcome you all to the one-week online FDP program on building knowledge-driven intelligent autonomous systems, generative AI, agentic AI, and edge AI, organized by the departments of CSE and IT, Andhra Laila Institute of Engineering and Technology. I, NVL Manaswini, Assistant Professor, Department of CSE, and I am delighted to be your host for today's session. I have the honor of welcoming our dignitaries, Reverend Father Dr. B. Jujireddy, SJ, Secretary and Director of the Andhra Laila Institute of Engineering and Technology, Dr. O. Mahesh, Principal of the Aliet, Reverend Father Dr. Emmanuel SJ, Assistant Director of the Andhra Laila Institute of Engineering and Technology, and conveners of the FDP is to head up the CSE and IT department, as well as the faculty of all the faculty members. A hearty greeting to everyone. Andhra Laila Institute of Engineering and Technology is a famous Jesuit institution that values academic excellence, ethics, and service. The college's strong standards for institutional performance and high quality education are reflected in this NAC A+ affiliation. Additionally, a number of departments are NBA accredited, indicating a dedication to outcome-based learning and ongoing growth. Strong engineering curricula, interdisciplinary research, financed projects and patents, and ongoing industry partnerships through MOUs are all provided by Aliet. It is delighted to sponsor national technical events, extension programs, student clubs, and innovation-driven activities. To improve faculty and student learning, we frequently host training courses, workshops, and FDPs. This FDP is being organized from 15th June 2026 to 20th June 2026 with the objective of enhancing knowledge in emerging areas such as generative AI, agentic AI, edge AI, automation tools, and private GPTs. We are fortunate to have eminent academicians and industry experts as resource persons throughout this FDP. Now, I would like to provide a brief overview of the FDP schedule. Over the next 6 days, participants will have the opportunity to learn from distinguished academicians and industry experts on emerging areas of artificial intelligence. Today, we begin with Dr. Chandra Mohan D from IIITDM Kurnool, who will speak on generative AI and LLMs, foundations, architectures, and emerging applications. On day 2, Dr. Smita Chaudhary from KL University will guide us through building OAG and multi-agent systems using free open source tools. Day 3 features Dr. K. Chandrasekhar from Aurora deemed to be University Hyderabad, who will deliver a session on agentic IAG and knowledge-driven autonomous AI systems. On day 4, we have two expert sessions. Dr. S. Vasuvi from VITAP will discuss the role of edge AI in modern space missions, followed by Mr. Prithvi Narayana, the data and AI engineer at TCS, who will demonstrate AI-driven workflows using the N8N automation tool. On day 5, Dr. B. Venkataraman, HOD CSC, IIIT Basel, will share insights on building private GPTs for organizations. Final day 6, Mr. K. Devarajulu, project manager at HCL Chennai, will conclude the FDP with a session on generative AI beyond prompting with real-time examples. We are confident that this FDP will provide valuable knowledge, practical exposure, and insights into the latest advancements in generative AI, agentic AI, and edge AI. Now I invite Dr. L. Kanyakumari, Associate Professor and HOD of CSE Department, FDP Convener, to address the gathering.
Thank you, madam. Good afternoon, all. I extend a warm welcome to our beloved Director, Reverend Father Dr. B. Jojireddy, SJ, Reverend Father Dr. S. Emmanuel, Director of Examinations, our esteemed Principal, Dr. O. Mahesh, the heads various departments, faculty members, and all my dear participants. Welcome you all. It gives me immense pleasure to welcome to this 1 week faculty development program on building knowledge-driven, intelligent, autonomous systems, generative AI, agentic AI, and edge AI, organized by the Departments of Computer Science and Engineering and Information Technology, Andhra Layala Institute of Engineering and Technology. We are honored to have with us an excellent panel of experts for academia and industry who will share their knowledge and practical insights on some of the most transformative technologies shaping the future of computing. On behalf of the organizing committee, I extend a warm welcome to all our resource persons and participants who have joined us from various institutions and has evolved rapidly from traditional machine learning systems to generative AI, agentic AI, and edge intelligence. Today, AI systems are not only capable of generating content, but also they are useful for reasoning, planning, collaborating through multiple agents, and operating efficiently at the edge. These advancements are creating unprecedented opportunities in education, healthcare, manufacturing, finance, space technologies, and other domains. The objective of this FDP is to provide participants with both technical understanding and practical exposure to these emerging technologies. I encourage every participant to actively engage with the resource persons, ask questions, participate in discussions, and make the most of this learning opportunity. The true value of an FDP lies not only in acquiring knowledge, but also building collaborations and exploring new research directions. I take this opportunity to express my sincere gratitude to our management, principal, conveners, co-coordinators, and my members of IT departments, and all resource persons for their continuous support and efforts in making this FDP a reality. Once again, welcome of you and wish you a productive, enriching, inspiring learning experience throughout this FDP. Thank you all and all the best.
Thank you, madam, for your valuable message and objectives of this FDP. Now I request our respected Dr. O. Mahesh, Principal of Aliet, to share his valuable thoughts with the participants. Sir, kindly address the gathering. Sir,
Reverend Father Dr. B. Jojireddy, Director of this institute, Reverend Father Emmanuel, Director of Examinations, Dr. L. Kanyakumari, HOD of CSE Department, Dr. Chandra, HOD of IT Departments, resource persons, participants. Good afternoon to every one of you. I welcome all the participants and resource persons for this 1 week online faculty development program on building knowledge-driven intelligent autonomous systems, generative AI, agentic AI, and edge AI. So this FDP program, I hope, will help all the faculty members to have some awareness and knowledge on artificial intelligence. Now, AI has become a buzzword. It is being applied to many domains. So earlier, so program writing and the way human mind thinks, both are considered to be totally different. The way human mind works and the way program is written. So there is no parallelism. And because of that, human minds are considered to be superior compared to the machines. So over the years, machines have been developed the way humans think. Since humans generate patterns based on the decisions to take, and machines are also programmed in such a way that they also identify from the data what are the patterns. Based on that, they can give decisions the same way as human being take decisions. Okay, this has been a research topic for a long period. So earlier, deviating from the traditional programming, expert systems have come into existence, okay, sometime back in the 80s. Okay, during that period, the way experts think based on the data, mission also was able to think in the same way and give its suggestions and its decisions, and they are comparable to that of an expert. So because of that, these systems were known as expert systems. Okay. Afterwards, the more advances have taken place, and now we'll see different versions of AI, generative AI, agentic AI, and edge AI. So all these mimicking the way human mind works. And people also say because of emergence of AI, there are jobs are lost. Many programmers may lose their jobs. And there are also some people say that they do not lose jobs, but they have to improvise, update their knowledge, and there will always be a place for skilled workers. So skill will enhance. So whatever may be the schools of thought, but one thing is certain for industry, because of advent of AI, the productivity has improved. So less skilled worker with the help of AI tools can work as a more skilled person. Okay, similarly, the things or the work that can be completed when you measure it in the time frame. So in less time, more work can be provided or more work can be done. So this way, productivity has improved, and the since productivity has improved, so all the people in industry and academics are interested to see that students who come out of the colleges who will become part of industry, they should also have awareness and knowledge about using the AI tools. I hope this FDP program will help all the faculty members to learn different AI tools. At the same time, this will also help to disseminate that knowledge to the students. I once again congratulate the HODs of CSC and IT departments and their team for taking up initiative to conduct this FDP program and drawing persons also from academics as well as from industry so that the faculty will get the advantage of knowledge. The faculty will gain knowledge not only from academicians but also from the industry people, and in turn they can transfer this knowledge to the students. I wish all the participants that this program will be more memorable and effective, and I hope that everybody will improve their knowledge. Thank you.
Thank you, sir. Thank you, sir, for your motivating words and guidance. Now, it is now my privilege to introduce today's distinguished resource person. We are honored to have Dr. Chandra Mohan D. is an accomplished academician and researcher currently serving as an assistant professor in the Department of Computer Science and Engineering at IIITDM Kurnool. He holds a PhD from NIT Varangas, specializing in machine learning based approaches for genomic data analysis and disease prediction. With over 8 years of teaching and research experience, along with industry exposure at TCS, his expertise spans AI, deep learning, bioinformatics, and data mining. Dr. Chandra Mohan has an impressive research portfolio with multiple high-impact SCR indexed publications in leading journals such as IEEE and Wiley. His work focuses on explainable AI, graph, neural networks, drug discovery, and healthcare analytics. He is actively involved in funded research projects, including a sponsored project on disease prediction and drug candidate generation. In addition to research, he has contributed significant to academic development through organizing FDPs, delivering keynote talks, and mentoring students. Known for his strong analytical teaching and leadership skills, he continues to advance interdisciplinary research at the intersection of AI and biomedical sciences. We are delighted to have him with us to deliver a talk on generative AI and LLM foundations, architectures, and emerging applications. Let us warmly welcome Dr. Chandra Mohan D. Without further delay, I request Dr. Chandra Mohan D to take over the session.
Okay,
Sir,
thank you, ma'am.
Over to you, sir.
Am I audible, ma'am?
Yes, sir.
Okay. Good afternoon to one and all. Thank you for inviting me for this session. So now, so I can share my screen. Yeah, someone please confirm is my screen is visible? Hello? Yes. If you have any like issue, please interrupt me. Then we can continue. Right. Today my topic is generative AI and large language models, foundations, architectures, and emerging applications. So as part of this, this is the outline of my session. In generative neural networks, I'm going to discuss generative neural networks. In generative neural networks, I need to discuss generative models and discriminative models. What is the difference between generative and discriminative models? Now then, before going to discuss generative models, how the generative models evolved, we should discuss. So yeah, before that variational autoencoder, one of the generative model, then we need to discuss autoencoders. So how autoencoders works and variational autoencoder works. Then we will go for one case study like a text generation using variational autoencoder. Next, generative adversarial networks like a GAN. Then one more case study we will discuss image generation. Now applications of GANs I'm going to discuss. Then quickly I'll introduce LLMs and their advanced architectures, emerging applications and challenges in LLMs. This is the overall plan for this session, first today's session. Now come to GANs, generative adversarial networks. Right, I hope I am clearly audible. Yes, right. Right. So before going to discuss these generative adversarial networks or generative models or generative AI, so the prerequisite for these things are first, I hope everybody know machine learning. In machine learning, like supervised learning, semi-supervised learning, or reinforcement learning, or unsupervised learning. Yeah, these techniques I hope everybody know. With that assumption, I'm going to discuss because those things we should know. Then next, in machine learning, we have different supervised learning techniques, unsupervised learning techniques. So then we will come to that discriminative models. Then if you come to deep learning, so we can say deep learning is a subsection or subset of machine learning. and which is a subset of artificial intelligence, Now come to supervised learning, those models, we can call it as discriminative models. Okay. So again, supervised learning, regression models are there and classification models are there. Right. Now, after that, come to deep learning, why we are moving to deep learning? What are the advantages of deep learning? That part, I hope you know. Otherwise, I'll touch a little bit, not a detailed way. Then in this again, deep learning, these artificial neural networks, next convolution neural networks, then back propagation, then in convolution neural network, after convolution neural network, recurrent neural networks, then in that LSTM, GRUs, all these terms are at least technologies, I hope you know, right? So now come to generative adversarial networks. Simply, these are neural networks. These neural networks contains maybe multi-layer perceptrons and convolution neural networks. Yeah, different GANs contains different neural networks. These are simple neural networks that can generate data, maybe text data, okay, like text data. We can generate signals also, like speech signals, and images also we can generate, music also we can generate, speech we can generate, or text, whatever it is, any type of data, this type of data, text, maybe images, like music. Nowadays, if you see, maybe you observed or not, generative AI generating music also, like songs also it is generating. Nowadays, that the tools are available now. Now, what GANs? GANs are part of machine learning only. GANs, we can say, part of deep learning, which is again part of machine learning. Okay, that can learn to mimic a given distribution of data. So the generative model, what exactly learns from the data is not exactly data. It learns the distribution of the data. It learns the distribution. How can we represent distribution? Okay, see, little for the beginners, it is looks very advanced. If already people knows all these things, it looks very simple. Okay, I need to like cover all the participants. So I have some flow, I'll go in that flow. We will go to advance also, don't worry. Okay, now distribution, like we saw maths somewhere, we studied probably we studied about distributions, like what is distribution, how can we represent distribution. Distribution may be uh, binomial, like if you see, like uniform distribution, okay, different distributions, Gaussian distribution, we can say different techniques, right? So in those, how can we represent the distribution? The distribution we can represent by using mean and standard deviation. So what is the mean of the data and what is the standard deviation? How the data is dispersed from the mean? With respect to those two parameters, we can say distribution. So someone is unmuted. Please mute it. If you have any query, you ask me. Unmute and ask me. Okay. So GAN first understands what is the distribution of data. Okay. From that distribution, it will pick some sample random noise. From the depth, it will generate data, whatever the data we want. Okay. So on which for which data we find a distribution. From that distribution, it will generate such type of data. Okay, such type of data. So with this, I hope, so for the beginners, you will not understand anything. Slowly you will understand when you move further what is the meaning of this statement. Okay. So GANs consist of two neural networks, very simple neural networks, which are not complex neural networks, very simple neural networks. One trained to generate data. Okay, it contains two like neural networks. One is, we can say, encoder, another one is, we can say, decoder. Okay, the encoder what it will do, it will generate data, or we can say generator discriminator. Two things are there. Again, if you come to GANs, generator discriminator is there. If you come to variational autoencoder, yeah, encoder decoder is there. But now you think there is one neural network which will generate data. Another neural network is there that will distinguish actual and real data. Actual means real data and fake data. Okay, what is the meaning of this? So we need to build the generated such that the generator should generate the data which is exactly like actual data. Okay, whatever the generated data we are generating, that is fake, obviously, but we should generate fake data in such a way that which is exactly same like actual data. Okay, actual data. So these two neural networks present in the GANs. Next, what structures that generate data, including GANs, are considered generative models, in contrast to more widely studied discriminative models. So, till now, like whatever the discriminative models we studied, the generative models are different from discriminative models. We should understand this discriminative versus generative model. Okay, so discriminative models are those used for most supervised classification and regression problems. Okay, so classification regression problems are discriminative models which will discriminate, okay, one sample from other sample, which will discriminate. So like supervised learning techniques, suppose to train a model to classify images of handwritten digits or binary classification, suppose you take dog and cat image, we should discriminate two images. Okay, so now take a regression problem. Suppose we will predict based on previous data, we will predict some continuous value. Okay, that also comes under discriminative models. Now take one example as part of discriminative models. Now you see here, discriminative models, what we will do, it contains, the data set contains labeled data. Suppose take handwritten digits here shown here. So handwritten digits, MNext data set is there. From that only it took these images. A labeled data set containing image of handwritten digits and their associated labels indicating which digit each image represents. Suppose if you take this image, the label is 9. If you take this image, label is 1. This image, the label is 2, and so on. What we can do here, we will take these type of images. We can build or we can train a discriminative model. We can train a discriminative model such that after training, if you give new class like image, handwritten digit image, which will predict what that handwritten digit written in this image. Okay, so this is a discriminative and which is supervised learning technique, right? During the training process, we use an algorithm to adjust model parameters. Suppose convolution neural network, you take it to build this discriminative model. In the convolution neural network, what convolution neural network will do? Convolution neural network takes input image and one more small like image, we can say, that is kernel or a mask, what we can say, kernel we can say. That kernel randomly initialize some values. Okay, randomly initialize some values. That a small kernel go through this input image, big image. Suppose this MNext handwritten digits image size is 28 by 28 image. Okay, grayscale image. It will go through this image and it will generate some convolved vector, and by using pooling like min average pooling or max pooling, we can extract the important convolved feature vectors. Again, we will send through one more convolution layer, pooling layer, convolution layer, pooling layer. Then finally, okay, flatten layer converts those small convolved feature vectors into one-dimensional vector and pass to fully connected layer. Okay, so this is the forward pass. So whatever the image you will give, finally we will generate one probability value for that image. Okay, See, this is a handwritten digit, okay, classification. So handwritten digit classification, 10 digits are there. Finally, at the end, in fully connected layer, in the last output layer, we use like a softmax, which will generate 10 probability values. Out of those 10 probability values, which probability value is more, the respective label we will assign to that image. Okay. So then we use some like a binary cross entropy, or here it is a 10 class classification problem. We use categorical cross entropy loss, and through back propagation, we can update the kernel values in case of convolution. And in case of convolution neural network, it contains two things. One is feature extraction stage. Those are convolution operations. Another one is that fully connected layer classification or regression task it will do. In the fully connected layer, or we can say it is, we consider as MLP, there the link weights are updated. And here in convolution, the kernel weights are updated. That's the meaning of, yeah, what is the, during the training process, we use an algorithm to adjust the model parameters. Okay, we are adjusting the model parameters. What are the model parameters in this convolution neural network is? One is kernel values, initially randomly initialized. Those values are updated. And in fully connected layer, like link weights are updated. Link weights and biases are updated. Okay, link weights and biases are updated. So in this way, discriminative model is trained. Okay, discriminative model is trained. The goal would be to minimize loss function. I told you we use categorical cross entropy loss. We need to reduce the loss. What is the meaning of reducing loss? So if you give one image to this convolution neural network, which will predict some probability values. Suppose the class label is 9, okay, which will generate 10 probability values. Okay, 10 probability values. Just give me 1 second. Online whiteboard, I will take it. Whiteboard. So just take. Okay. So it will generate 10 probability values. I'm not going in detail. 0, 1, 2, 3, and so on. 9 labels are there. Suppose it generated probability 0.1 per. So if you give an image, suppose the image contains like this, just imagine like this. So it is actually 2. Okay, it look like somewhat 3 also. So my model is predicting like the probability this image belongs to 0 digit is 0.1. Suppose this is 0.0 and this is 0.5 and so on. Like this, total probability sum should be 1 only. So again, this 0.3, okay, for 3, okay, like this. And this is 0.0, like this. Probabilities it will generate. Suppose 0.5 is highest, which is saying my model is saying 0.5 probability is there. This handwritten digit belongs to class 2. Okay. So then this is correct. Sometimes suppose this is 0.3 given, this is 0.4 given. Okay. So what my model is saying, this image, whatever the handwritten digit is there, 0.4 probability is there, which belongs to 3, digit 3. Okay, this is wrong prediction, right? Wrong prediction. So based on correct prediction, wrong prediction, I already know that this class label of this image. So I'll compare. So 0.4, what is the highest probability generated for particular digit? I'll consider that digit. This is 2 and this is 3, predicted as 3. This is wrong. Okay, this is wrong. So like that last value, I'll come to those formulas also. In generative models also, we use same formulas. So I'll come to that. So that loss we can calculate and we'll try to reduce the loss. We'll try to reduce the loss. The goal would be to minimize the loss function so that the model learns probability distribution of the output given the input. Okay. So now after training phase, I'm talking about discriminative models, not generative models. We use the model to classify a new handwritten digit image by estimating the most probable digit. Suppose this is discriminative model. Actual image I sent like this. This is actual digit is 5. My model also predicted as 5. Okay. So like this, we can do discriminative models. First, we will give input and class label, and we will try to reduce the loss. We train the model. After my model is giving best result, somewhat like up to 95 or something based on the task that accuracy we will decide. And then we keep that model for testing the new digits, new handwritten digits. This is discriminative. In mathematical term, discriminative models learn the conditional probability. Okay, please check this. Probability, conditional probability, what this conditional probability says, given X, what is the Y label, we will predict it of the output Y for the given input X. This is conditional probability. Besides neural networks, other structures can be used as a discriminative models such as logistic regression models and supportive vector machines and so on. Okay, so these all comes under this logistic regression and support vector machine, all comes under classification models. These are not exactly neural networks, other models. Now come to generative models like GANs. Okay, however, are trained to describe how a data set is generated in terms of probabilistic model. Look, from the input data, we'll try to understand the distribution of the input data. So then we'll try to map that distribution to standard normal distribution. Okay. So we will see that theory only I'm discussing. Now we will go slowly. By sampling from generative model, we can generate new data. By sampling, what it is saying, generative models at the time of training, just to take it at the time of training, it will try to understand the distribution of the input data. Then what it will do, by sampling from the generative model, we can generate new data. So whatever the distribution that generative model generated, from that we can take some sample, random sample, and we can generate new data. Okay, we can generate new data. Okay, while discriminative models are used for supervised learning, generative models are often used with unlabeled data set. We can say unsupervised learning, one type. Okay, can seen as form of unsupervised learning. Okay, so not exactly, but we assume like unsupervised learning. Using the data set of handwritten digit, you could train the generative model to generate new digits. Okay. There, what we are doing, just to understand the example only. There, what we are doing, we are giving handwritten digits, and we are training the model. The trained model is used to test the handwritten digit, what is written in that image. Okay, but in this case, what we are doing, we are using these images and we are finding the distribution. Then after finding the distribution, random some sample I'll take from the distribution. By using that random sample, I'll try to generate the image or text, whatever it is. So here we are not predicting class label, all this. We are trying to generate that handwritten digits. Okay. Now, like during the training phase in generative models, we use some algorithm to adjust the model parameters to minimize the loss function. Here, model parameters means that mean and standard deviation. Okay. So for each handwritten digit, the distribution come close. Okay, come close. But suppose all 9 handwritten digits images, the distribution comes to one region. For all one handwritten digit, the distribution come close to one region, and so on. Okay. So what we are trying to do here also, we are adjusting, minimizing the loss and learn the probability distribution of the training set. So what is the parameters here? Their parameters are that CNN, like kernel values and fully connected layer, like link weights, all those things. Here, so the mean and standard deviation. Mean and standard deviation are the parameters. Okay. Then with the model trained, we could generate new samples. Now by using this, okay, by using this, we can generate the model, means we can adjust the parameters. Next, random data, I can take it. Okay, random data, I can take it. I'll give as input to this model, it will generate, okay, it will generate new image. Unlike discriminative models, generative models learn the probability of the input data X. That is conditional probability. This is probability. It will try to understand the probability. Now, and by having the distribution of input data, they are able to generate new data instances. From this whole story, you should understand only 1 or 2 points. First point is, in case of discriminative models, we can train the model and we will predict the class label, or we will predict the continuous value in case of regression. Okay. But in this case, we will try to understand the distribution of the input, and then from that distribution, after finding the distribution, from that distribution, I'll take random data and I'll try to generate the samples. Till now, do you have any doubt? Hello? Hello, sir. Madam, am I audible?
Yes, sir.
Yes, yes. Till now, do you have any doubt? Because I explained in the broad view, specific deep, I didn't went. I will go next slides. So this is about discriminative and generative models. If you don't have any doubt, I'll move further. Now come to generative models. Besides GANs, generative adversarial networks, there are various other generative model architectures such as Boltzmann machines. Maybe you listen this Boltzmann machine. Next, variational autoencoders. Next, hidden Markov models. But in this session, I'm focusing on variational autoencoder only. So variational autoencoder. So what is autoencoder? First, we'll try to understand. Then quickly we will move to variational autoencoder and how this variational autoencoder works like a generative model. Okay. So now autoencoder. What is the autoencoder? Autoencoders are again special type of unsupervised feed forward neural network. I hope this word feed forward neural network, you listen somewhere, that is MLP only. In MLP, if you know MLP, multi-layer perceptron, what it contains, these are input, it will take here. Suppose hidden neurons are like this, and this is output neuron image. Imagine. So like this, for every input data goes to each and every neuron, like this. Yeah. Right, like this, from here to here. This is feed forward neural network. MLP is feed forward neural network, where input takes here, and it will go to this neuron, this neuron, this neuron. Only input data is forwarded. Okay. This one we can say fully connected feed forward neural network. MLP is fully connected feed forward neural network. This autoencoders are one type of feed forward neural network. Feed forward means data forwards in the one direction, forward direction. Okay. Now in the backward direction, we can update the parameters. So now come back. So autoencoders are special type of unsupervised feed forward neural network. There are no class labels involved in this autoencoders. The main application of autoencoder is to accurately capture the key aspects of the data, to provide a compressed version of the input data, and generate realistic synthetic data. Now to understand this, what is the meaning of these two sentences? So autoencoder contains two parts. One is encoder, another one is decoder. What is the main goal of autoencoder is it takes input data, and from that input it will pick the important aspects or important points. Then it will convert that big input data into small input data, means compressed version, which contains important information only. Then from that converted, compressed or important information, by using that we will send to decoder. What the decoder will do? Decoder will again convert the like compressed input into actual input. Try to convert in the form of actual input. Means what we are doing? We are taking small compressed input and we are trying to generate synthetic data. Synthetic data means fake data, false data, we can say. So that generated output should be very similar to the given input. Okay, given input. So this is the main goal of autoencoder. Okay, autoencoders are compressed. Okay, so what it contains? Just 1 second, it's disturbing us. Okay. Yeah. So to keep fully connected feed-forward neural networks. Now I hope you understand that what is fully connected feed-forward neural network. Fully connected means for every input to every other neuron, the input is passed like it is a bipartite graph, if you say. From one layer to other layer, it contains all the connections, possible connections, and data is passed in forward direction. So this encoder contains two fully connected feed-forward neural networks. What this autoencoder? First part is encoder. So what is that encoder? Encoder compresses the input data to remove any form of noise and generate the latent space, okay, or bottleneck. So the encoder is a fully connected neural network. See the architecture, you see, you will understand. This is the encoder. So it will take input, maybe that input is image, or maybe that input is text, maybe that input is or signal, whatever it is, okay, biological data, whatever it is. So anyhow, every input data we can convert into numerical vector. That numerical vector, it will take it will pass to neurons, and from here it will convert. Here when I say neuron, what neuron contains? Neuron contains two functions. One is so one is like what we can say, which will perform like sum of products format. Okay, linear function we can say. Another, the same neuron contains nonlinear activation function. What this will do, it will take all the inputs and the corresponding link weights, it will multiply that input. Suppose if you take this neuron, it will take input from 4 nodes. Those are not neurons, only it will take input and it will send to these neurons. So from 4 nodes, it will take input and it will multiply that input with the link weight. That link weights are again randomly initialized at the beginning. Then what randomly initialized, later we can update those link weights. Training the model, means we should adjust these link weights only. We should adjust these link weights only. Yeah, we will come to that. Suppose this neuron contains nonlinear function and linear function and nonlinear activation function. I am assuming that you know on nonlinear activation functions like sigmoid, which will take input, any input, okay, and which will convert into like value output between 0 and 1. And suppose tan h, which will take that linear function output and generates output of nonlinear activation function tan h is -1 to +1. And sigma, what is that ReLU, which will convert negative values into positive and positive values keep it as it is. Leaky ReLU, so many ReLU, like different ReLUs are available. So this is my encoder. It will take huge input and reduces to small output, that we can say latent space. It is not generating, which is converting. Okay, which is not generating, which is converting. Okay, so huge input into small output, it will convert. Next, what this decoder will do exactly, like a mirror of this encoder, if you see. So it will take this small input. This is the output with respect to encoder, input with respect to decoder. This input it will take and try to convert or try to reconstruct the actual data. Okay, reconstruct the actual data. So now come back here. Decoder making use of only the compressed data representation from the latent space tries to reconstruct with as much fidelity as possible as original input data. Okay, this is the decoder responsibility. So encoder will convert it. If you see, if you know, in computer science, everybody's I hope computer science faculty, you know, compression and decompression. Okay, will convert. Will take a huge data and compress into small data, and again we will decompress it, or we can say encryption and decryption. Okay, when sender receiver architecture, I can encrypt the data and decrypt the data at receiver. Similar way this encoder decoder works, but different way. Similar looks like similar. Right? Decoder takes that small latent vector and try to reconstruct the data as much as similar to the input data. Okay, as much as. It is not generation, it is reconstruction. Okay, the architecture of this neural network is therefore generally mirror image of the encoder. Okay, the goodness of this prediction can then measured by calculating reconstruction error between the input and output data using loss function. So what we are going to, how can we measure how much this decoder is autoencoder is effective means whatever the input we are getting, the similar type of output we will try to generate. We will try to reconstruct. So how much this reconstructed output is differentiate from the input, that is the loss. By using the reconstruction loss, we can train the model. Okay. So we can train the model means whatever the link weights are there, we can adjust it. Because why we are adjusting link weights only? Because input we are not going to change and output is not in our hand. Okay. So we only thing hyperparameter we can adjust is these weights, link weights and biases, repeatedly, iteratively repeating. Hello.
అంతకుముందు ఓన్లీ రిపోర్ట్ సబ్మిట్ చేస్తే అయిపోయేది. ఇప్పుడు వాడు 2 minutes వీడియో కూడా అడుగుతున్నాడు.
Madam,
video
I hope someone is unmuted.
All the participants, please
Events
be
like
muted.
workshops, seminars, guest lectures.
I think
Please
host
be
can
muted.
mute them.
చెప్పించిండట మా వాళ్ళకి ఆల్రెడీ 4 members మళ్ళా డేస్ తర్వాత మళ్ళా డెమో అయిందని చెప్పినారు.
Hello, madam, please mute yourself.
అడిగినట ఈ మధ్యలో ఎక్స్చేంజ్ కలిసిరట.
I hope host can mute them. Yes. Shall I continue?
Yes, sir.
Yes, thank you, ma'am. Yes. Now, repeating iteratively this process of passing data through the encoder and decoder and measuring the error to tune the parameters through backpropagation. Okay. So this is the autoencoder architecture. This autoencoder architecture, this image I took from actual paper who proposed this autoencoders. So now you see in general, the encoder can be this image handwritten digit it will take encoder written as a function g that will depend on some parameters. Suppose hi like a latent feature or compressed features. This is the compressed one. So hi here, hi we can generate by using a function g x of I. So this function is MLP, multi-layer perceptron we are using. Finally, we will generate some, or we can say some type of feed-forward fully connected neural network. Now, how this decoder function works? This decoder takes hi as input, and the decoder function takes hi as input. Okay, and x it tries to generate.
FDP register అయినా
It try to generate
వింటూ
output
ఇక్కడ చేయాలి.
xi tilde. Okay, xi tilde. My actual input is xi. My output is reconstruction output is xi tilde. Okay. What we try to mathematically we try to do arc minimize what we are trying to minimize the difference between xi and xi tilde. What is xi tilde? Xi tilde is equals to f of g of xi. We need to try to reduce the difference between these two. Okay. We need to minimize this difference. Okay. To minimize this difference, we need to adjust these functions. What are the functions? Here it is a neural network. Here it is a neural network. How to adjust these functions? By adjusting the parameters. Which parameters? Weights and biases. So like this, it is defined. Okay, this is the mathematical representation. I hope all are faculty. So yeah, how can we formulate problem? We know in this way we can formulate the problem. So now autoencoder, some more points related to autoencoders. If an autoencoder is provided with a set of input features completely independent of each other, then it would be really difficult for the model to find a good lower dimensional representation without losing a great deal of information. Okay, so it is a lossy compression, we can say. Autoencoders can therefore also consider as dimensionality reduction technique. So autoencoders we consider as a dimensionality reduction technique because we are taking huge input and converting only important input. So the same thing we can do in dimensionality reduction technique. We will take so many features by using principal component analysis. We will take only important features. Similar way, we will take important input only. Additionally, which works like a compressor. Okay, autoencoders works like a compression technique. So other compression techniques, this also working like a compression technique. So which is taking huge data and generating a latent vector of small. Okay, that also we can use. So autoencoder we can use to reconstruction, or we can use for dimensionality reduction, or we can use for compression. So in the autoencoders, if you observe, what are the adjustable parameters? Some of the most commonly hyperparameters that can be tuned when optimizing your autoencoder. What are the hyperparameters? See, there are difference between hyperparameters and learnable parameters. Okay, learnable parameters. Hyperparameters are these. What are the hyperparameters? The number of layers for the encoder and decoder neural networks. So here, if you see, number of layers, only 3 layers are there for a decoder. And for encoder also 3 layers are there. This is the first layer, input layer, hidden layer, output layer. Now for decoder case, this is input layer, hidden layer, output layer. So the number of layers, if you want, you can increase it. That is hyperparameter. The number of nodes of each of these layers. Yeah, same way, Here only 3 neurons I used, 4 also I can use it. Here 1 neuron I used, 2 also I can use it. Like this, number of neurons. The last function to use for the optimization process, like binary cross entropy for like classification or mean square error for regression tasks. So the size. Now the size of the latent space. So the size, latent space, how much size? That also we can fix it. Well, these are hyperparameters. Learnable parameters in this encoder decoder is like edge weights and biases. Edge weights and biases. So finally, autoencoders can be designed to work with the different types of data, like a tabular, time series, image data. Therefore, we can design to use a variety of layers such as convolution layers for image analysis. Okay, this is about autoencoders. What are the last functions we use generally in classification regression problems? Mean square error we can use. Mean square error means suppose the prediction value, suppose if you are giving some input and predicting some output, okay, for the given input already actual class label is there. That is the actual class label. Someone is disturbing continuously. Stop sharing. If possible, I'll mute them. Okay. Okay. This is my actual class label and a predicted class label. So for more samples, so 1 into n samples, xi minus xi bar whole square, average value, I'll take it. This is mean square error. At the time of training, we use this mean square error. Next, binary cross entropy. If you see binary cross entropy, we used for classification if it is a binary class classification. Okay, like that last, how can I calculate? Minus, why we use minus? Because here log is there, which will generate negative value. So we use minus here. That minus and this minus becomes like positive. So 1 to n samples, xi means actual class label. Some formulas, some books they'll give yi log, yi cap, nothing, not a problem. This is xi means actual class label, log xi cap means predicted class label, plus 1 minus xi log 1 minus xi cap. This binary class entropy we use it. So mean absolute error, sometimes we use it instead of mean square error to calculate the loss. If you take mean square error, it is a square is there. Sometimes the loss value becomes very huge. To overcome that, we use absolute value instead of square value. So more robust for outliers. Suppose for outliers, this will create some issue. The training, model training deviates. To overcome that, we use mean absolute error. Now come to autoencoders. Till now, it is not generative AI, what we discussed, autoencoders. Those are not generative models. In that autoencoders, different types of autoencoders are there. So one under complete autoencoder, sparse encoder, all these encoders are there. In this one, I am interested in variational autoencoder. In this, I am interested in variational autoencoder. So what variational autoencoder? What is the difference between normal encoder and variational autoencoder in real life applications of autoencoder? Okay, what are the real life applications? Just now I told image compression, denoising. Image compression means I'm taking important input from the actual input. So means indirectly what I'm doing, I'm compressing and I'm doing denoising. Okay, I'm removing noise. What is noise? Noise is, I'll just switch off my camera. Like what is noise is in the input which is not much important, that is noise. Okay, One of the main applications of autoencoders is compress images to reduce their overall file size while trying to keep as much of the value information as possible, or restore images that have been degraded over time. Now, anomaly detection. Anomaly detection means, since autoencoders are good at distinguish essential characteristics. Suppose you train the autoencoder and now one input came, that is the anomaly. So which will deviate, which will identify it, If an image has been photoshopped, if there are unusual activities in the network, so which will do that also, anomaly detection also it will do. Next to data generation. Autoencoders means here variational autoencoder I'm talking. Data generation means variational autoencoders and generative adversarial networks are frequently used in order to generate synthetic data, fake data. Okay, realistic images of the people. Suppose nowadays, if you see, so many images are generating, that very common one is our images itself, people are generating. Okay, face images are generating. Now come to variational autoencoder, how training will happen and how testing will happen in variational autoencoders, we will see. Variational autoencoders are generative models. Autoencoders, normal simple autoencoders are not generative models. So those are reconstruction models. These variational autoencoders are generative models used in deep learning to generate new data in the form of variations of the input data they are trained on. Okay. First, we need to train the variational autoencoder. Okay. Training means we should try to derive the distribution, or we try to understand the distribution of the input. Okay. We should try to understand the distribution of the input. Okay. They also perform tasks common to autoencoders, like whatever the operations the autoencoder will do, it will do this variational autoencoder also, such as denoising, compression, all those things. Along with that, these are generative models. These will generate new data also. Like all autoencoders, variational autoencoders also composed of an encoder and decoder. Okay, same like encoder decoder it contains. Okay, now an encoder that learns to isolate the important latent variables from the training data. Here, it is not directly generating latent vector. What it is doing, it is trying to identify latent variables from the training data. Latent variables. Their latent vector it will generate, here latent variables. So a decoder that then uses these latent variables to reconstruct the input data. Okay. So latent variables are, like I told, mean and variance. Okay. So what encoder try to do, it will try to identify the mean and variance of the input data, which means it will try to understand the distribution. Okay. Then that from that distribution, it will take mean and some variance, and it will try to generate new data by the decoder. Now, variational autoencoder, however, whereas most of the autoencoder architecture encode a discrete fixed representation of latent variables. Yeah. Other encoders, what it will do? Fixed representation of latent variables, or fixed vector it will generate it. Okay. But variational autoencoder encode a continuous probabilistic representation of the latent space. So, what is the meaning of this? Okay, what is the meaning of this is? So, in normal variational autoencoder, fixed vector it will generate like this. Okay, but in this variational normal autoencoders, this is the scenario. In variational autoencoder, what it will do? It will try to find this mu and sigma. Okay, sigma and mu. Okay, sigma and mu. So meaning, what is the meaning of this? This is the distribution. Okay, this is the distribution. Mu sigma says this is the mean and this is the distribution from the mean. This is the distribution from the mean. So it will find that continuous, okay, continuous and probabilistic representation of the latent space. So this enables a variational autoencoder to not only accurately reconstruct the exact original input. So if you give one input to the encoder, the decoder in the variational autoencoder also reconstruct it, okay, but also use variational inference to generate new data samples that resemble the original input data, okay. So we will see, while variational autoencoders are frequently discussed in the context of image generation, okay. So image generation we use it, text generation we use it, and so on. They can be used for diverse AI applications, from anomaly detection to generating new drug molecules also. Okay, new drug molecules, chemical molecules also we can generate. Actually, in our research, we are using like very advanced generative adversarial networks for molecular generation. So not only sequence molecule generation, structured like graphs also we are generating. Okay, graph molecules also we are generating. So that much advance is happening nowadays. Variational autoencoders. What is latent space? So what is the meaning of latent space? So we discussed the collective latent variables of a specific set of input data. Okay, latent space means, so whatever the variables that those variables information, we can say latent space. Latent variables are underlying variables of the data that in the form that inform the way the data is distributed but are often not directly observable. Okay. From the images, we will not understand but, the distribution, which will identify the distribution. Okay. For a useful visualization of the concept of latent variables, imagine a bridge with a sensor that measures the weight of each passing vehicle. Okay. Now you see, this is the example. What is the latent space? Okay. What is the use of latent space? But suppose there is a bridge, some vehicles are passing over the bridge. There are some sensors. There are some sensors. Okay. For a useful visualization, suppose we don't know, there is no specific camera near that bridge, only but weight sensors are there. Weight sensors are there. So now some vehicle is passing over that bridge. This weight sensor will give some weight. Okay, weight sensor will give some weight. Based on that weight, we will predict the vehicle, which type of vehicle it is, which type of vehicle it is. So like this, from the observable data, we will predict unobservable data. Okay, that is about the latent space. Because there is no camera, we have no way to detect if a specific vehicle is convertible, sedan, van, or truck. So this example thus entailed two random variables, x and z, in which x is directly observable variable, which are vehicle weight. Z is the latent variable of vehicular type. Vehicular type. So by taking this as an input, from the input data, we'll try to observe some variable, that is latent variable. So from that latent variable, we'll try to reconstruct or we will try to generate new data. Now you take this variational autoencoder architecture. Very simple. If you see this, if this is not there, this distribution of latent vector is not there, it is exactly like a simple autoencoder. But in this, that encoder will try to identify two things. One is mu and variance. Okay. From this mu and variance, suppose from this mu and variance, but suppose this is the distribution, imagine. Mu is here, mean, and variance is from here to here, imagine. From this, I'll take some sample, like some vector I'll take in this distribution. From that, this is the latent vector generator. From this vector, the decoder will try to reconstruct the original image our original input or generate the image. In the training process, what will happen in the training process, I'll explain. So the input it will take, suppose input is the image, convert it into numerical vector. That numerical image input vector we took, encoder we are sending. We will predict that mu and variance, and this latent vector I will take from this mu and variance from the distribution. It will send to decoder. It will try to reconstruct it. So now at the time of training, we can do only reconstruction. We can do only reconstruction. By using reconstruction laws, then what we can do, we'll try to do, there is another loss, I'll discuss that, the KL divergence loss. By using reconstruction loss, we will try to adjust this mu and variance. Over a period, this mu and variance values properly adjusted. So from that distribution, the distribution is properly adjusted. From the distribution, whatever the latent vector you can take it, it will reconstruct the synthetic image or reconstruction image, very similar to input image, which is very similar to input image. In this way, it will work. In this way, it will work. Now, come back here. Variational autoencoder network. So now you see, variational autoencoder network, P, Z given X plays a crucial role, and it is also referred to as encoder. This networks take input data X and output statistical parameters like mu and variance, okay, associated with the latent vector Z, So what we are doing, we are predicting the mu and variance given input X. From this mu and variance, by using this, we can sample some latent vector. We can sample from that latent vector. This process can be understood as mapping the input data to specific distribution in the latent space, from which the latent vector is obtained through sampling. Sampling means random sampling, we can obtain it. So that how we can obtain Z we can obtain given X from normal distribution. Okay, from this, assume that that is a normal distribution. Okay, normal distribution, mu and standard deviation. Now, what is the latent space? Just we discussed. The primary training objective for any autoencoder is for it to learn how to effectively model the latent space of a particular input. Okay. How do variational autoencoder work? So now variational autoencoder work. Variational autoencoder differ from other autoencoders because of its unique way to encode latent space. So I'm reading some theory. Don't worry, because this theory is the main part we need to understand. So then we can understand mathematical equations. The different use cases to which their probabilistic encoding can be applied. Variational autoencoder encode latent variables of training data not as fixed discrete value Z, but as a continuous range of possible expressed as a probability distribution, P of Z. In Bayesian statistics, this learned range of probabilities for the latent variable is known as priori distribution. Indirectly, this encoder in variational autoencoder, encoder module try to understand the priori distribution. In variational inference, the generation process of synthesizing new data points, this priori distribution is used to calculate posterior distribution. Okay, so P of Z given X. In other words, the value of the observed variables X given a value for latent variable Z. Okay, so yeah, from these 3 points you go through. First, this variational VA is the encoder try to understand this mu and standard deviation. From that, this mu and standard deviation is the distribution for latent vector, Now, decoder, what it will do, by randomly sampling from within this range of encoded possibilities, Variational autoencoder can synthesize new data samples that, while unique or original unto themselves, resemble the original training data. Meaning is, so from the distribution, we can randomly sample what is that latent vector. From that latent vector, we can generate new samples. So now here there are two types of loss functions we use in variational autoencoder. One is reconstruction loss, another one is KL divergence. Reconstruction loss and KL divergence, two things we use. So reconstruction loss and KL divergence means pullback labeler divergence. What is reconstruction loss? Reconstruction loss is either we can use cross entropy loss or mean square error loss. Okay. The reconstruction is, this loss measures the difference between original data and the data reconstructed through variational autoencoder. The goal is to make the reconstructed data as similar as possible to the original data. So we can use either mean square error loss or cross entropy based on our task, or anything we can use it. Now KL divergence. What is KL divergence? This KL divergence term measures the difference between the distribution of latent variables generated by the encoder and the predefined target distribution. Okay, what is the meaning of this? So we are predicting mu and standard deviation or variance. That variance, two variables, I'll compare with the standard normal distribution. Standard normal distribution means normal distribution, we know mean and variance. Mean is at peak. Okay, variance, both sides are equal. But a standard normal distribution means where mean is 0, variance is 1. We are trying to compare the identified distribution as very close to standard deviation, or we will try to bring the distribution of the input very close to standard normal distribution. So how much this standard normal distribution, like how much mu is close to 0, how much standard deviation is close to 1. That difference we can calculate by using Kegel divergence, and we'll try to adjust that. In variational autoencoder, KL divergence is used to measure how much the learned latent variable distribution approximated by the encoder diverges from the priori distribution PZ, which is often assumed as standard normal distribution, where normal distribution mean equal to 0, standard deviation equal to 1. KL divergence ensures that, maybe some participants feels that it is theory, too much theory. No, theory plus mathematically I'm explaining the concept, then we will go for program. Okay. So without understanding mathematical intuition of any deep learning model, coding becomes very difficult, and it becomes like without basics. So if you go for directly program, it becomes meaningless. So you should understand mathematically and the theoretical part, then you go for program, then it becomes easy. Now KL divergence, what is reconstruction loss will calculate? Here we are using two loss functions. We are trying to try to reduce two losses. Okay, one is reconstruction loss, where the actual input is the reconstruction in output is how much deviated from the input, that is reconstruction loss, and how much the distributed or encoded distributed parameters is differed from the standard normal distribution parameters. This KL divergence will calculate it. The KL divergence ensures that the model does more than just accurately reconstruct the data. It organizes the latent space in a way that facilitates the generation of new data. At the training time, these two things we are doing. After training the model, that the encoder is not required. Only decoder is required. From the random distribution space we know, from that distribution space, we can take latent vector. Okay, we can take latent vector. From that latent vector, we can generate image or we can generate text and so on. In other words, it acts as a regularizer for the latent space, ensuring that similar data points are located close to each other in the latent space. Okay. So now meaning is that KL divergence tries to bring similar data points close to each other and diverse data points goes separated. Okay, goes separated. Now this is the KL divergence formulation. How can we calculate KL divergence? KL divergence, probability of Z given X and the probability of Z. Posterior probability and priori probability. Okay. Posterior probability and priori probability. Like we try to reduce this by using these formulas we will do. And in simplified manner, we can do this we use this formula 1/2 variance plus mean square minus 1 minus log mean variance. By using this formula, we calculate the what we can say loss, KL divergence loss. So once these two losses are calculated in the training time, at the time of training time, we try to reduce these two loss. Trying to reduce two loss means, so the latent distribution becomes very good and finally reconstruction becomes very good. After training, then no need, two things we can do. One, we can give input to the encoder and we'll try to reconstruct it. Or other thing, without using encoder, directly in the data distribution, random sample, I'll take it and try to generate text or image for the input. No, not input, it will generate data. So that's where we can say generative model, variational autoencoder is a generative model. So till now, do you have any doubt? Hello?
Sir.
Any doubt till now?
No, sir.
Okay. Yes. Fine. Next question is, sir, you are saying reconstruction. I'm taking one image. I'm reconstructing the image. Okay, where it is useful? Where it is useful? Suppose, so before going to generative adversarial network GANs, so this is one image. Why reconstruction is required? Okay, why noise removal is required? So a photographer, young photographer captured photos in a rainy day. He got this. Now he want to remove this noise that raindrops. He want to remove. Actual, he is interested about that location, not about that raindrops. Okay, how to reconstruct the actual image? This is a noise image. How can we reconstruct the actual image? Imagine our model is trained on the images, so many trained actual images. If you give this image, which will remove noise and it will generate actual image, Okay. So for this advanced generative models are GANs, generative advanced neural networks, for generative adversarial networks, GANs. Okay. So what I'm going to discuss in GAN, till now I discussed discriminative model, generative model difference, and autoencoder, variational autoencoder. How variational autoencoder work like a generative model. Okay. Now in this, already we discussed discriminative and generative models. I'll skip this part. And the details of generative adversarial networks. What are the components in the generative model and the discriminative model? Okay. Components of generative and discriminative model. Architecture. What architecture? Loss function, training, challenges of GANs, now types of GANs, uses of GANs, and recent applications of GANs. This I'm going to discuss here. We already discussed discriminative and generative models. Okay. So now GANs is a type of deep neural network model that are GANs are used to generate new data that is similar to the data it was trained on. Yes, that is important. Which will generate the data which are close to the trained data. Okay, which are close to the trained data. Okay, whatever the input you give, testing time, our testing time, reconstruction we can do in variational autoencoder, but in generative models, we try to train the model. After that, if you take random sample, it will try to generate the data very close to the input what we given at the time of training. Okay, what we given in the time of training. Now, the components of GAN. Okay, components of GAN. This is different. Okay, from variational autoencoder. GANs. GAN contains two neural networks. One is generator, another one is discriminator. Generator and discriminator. What is generator will do? What is discriminator will do? Their encoder, decoder. Here, generator and discriminator. Okay. GANs were inspired by the game theory. What is generator will do? Responsible for creating new data, So before going to discuss this, what I can do, I will go for one example case study. How can we generate text by using variational autoencoder? Okay, I'll go to Google Colab. So text generation in variational autoencoder. Right now, PyTorch code we did here. Actually, I didn't write this code. I took this code from some site only, right? So now I'm importing PyTorch packages and a neural network, functional F, data from the torch.utils.data. I'm importing data set, okay, data loader, import random, all these things I'm doing. These are packages, importing packages. Now I'm creating some dummy data. So this is a dummy corpus text data. Suppose we first need to train the variational autoencoder. Then if you give something, if you ask something, it will generate some text. Okay, generate some text. So this is my input, random input. I love machine learning, deep learning is powerful, NLP is fun, all these things. In this, NLP also involved. Okay, NLP also involved. Deep learning also involved, because in pre-processing, we need to do embedding. Okay. Now, vocabulary and tokenization. What we can do, each word, we need to give some numerical value. From that numerical value, we need to convert into numerical vector. Those things we have to do. So word to vec, word to vec is there, which will convert the given words into numerical vector. What we can do, simple terms, I'll explain that. How can we convert in the form of numbers, words in the form of numbers? What we can do, hold the corpus. This is corpus, means an NLP term. Hold this corpus, we can calculate the frequency of each word. Okay. So and we can arrange the words in the decreasing order of their frequency. Okay. So I'll rank the words based on their frequency. Highest repeated word ranked as 1, lowest repeated rank marked as some number, some rank is given. So what I can do, this is an English corpus only. These words we given some ranks, and each word is represented with that rank. Suppose this I repeated so many times. So the rank is 1. I represent as 1. This love is repeated as very less number of times. Rank is something like 30. Machine repeated only once. Rank is something like that. So this is small corpus. If you go for a very huge corpus, we can get so many frequented words and we can assign these numbers, these words in the form of numbers. And each number also we need to convert into embedding vector. Okay, embedding vector. This is the dummy corpus. You can see. So here we vocabulary we did it. Vocabulary size 20. Vocabulary size is number of unique words. Yes. Yes. So 20 unique words are there. Okay. Now what we are doing? Yeah. See some sentence. Okay. If you see that we can convert it like this. We can convert it this first data set 0 means this one. We can convert it like this. We can convert it like this. Okay. So now numeric vocabulary size is 20 means each sentence we need to convert into 20 length vector. First few words I can represent with actual ranks. Remaining suppose only 20 length I need to convert, only 5 words are there. First 5 are numbers, remaining all are zeros like this.
One is just
Yes, madam. I think someone is asking doubt. I'm not going line by line because it will take a lot of time. I need to cover topics. Okay. So see, overall, the sentence is converted in the form of numbers like this. Okay. Now, lot of code is involved here. So then what we can do, these numbers converted into numerical vector, like a 10 length vector, 13 is converted into 10 length vector and 5 also converted into 10 length vector. The overall, the sentence converted into, suppose this length is 20 and this each number is converted into 10. So it becomes 10 by 20 vector, 10 by 20 matrix. So that we can send as input to variational autoencoder. So this is the last function. Both are there. One is uh, reconstruction loss and KL divergence is there. So both loss we are calculating. At the time of training, we can calculate this loss. Now you see here, we are training the model. Yeah, in first epoch, so what it is, loss is this much, second epoch loss is this much, and so on. For 20 epochs, loss is reduced to somewhat. So now text generation. Okay, text generation means this is one so sentence text like this is 4 by 1, 2, 3, 4, 5, 6, 7, 8. Okay, 4 by 8 length vector. 4 by 8 length vector. So corresponding numbers are like this, corresponding numbers are like this, and the corresponding text is like this. NLP, I, fun, I, love. Yeah, because we trained on small data set is giving random values. So now if you take whole model, yeah, just input is, when I give input, I enjoy working on AI. It is rewritten like this because it is giving wrong. Why? Because it is giving wrong because we took very short input. Okay, very short input. Reconstruction input, if you give this output, it is generating like this. Over a period, it will try to generate a similar type of output, Okay, similar type of output. So don't worry. So what code saying is, first in this you need to understand one point. First, if input text is given, how we need to convert into numerical values, and how can we generate latent vector, and how to pass to variational encoder, then how to reconstruct the things. Okay, two things are there. One is reconstruction is there. This is the generated text. This is the generated text. What I'm doing, I'm taking some random values like this. I'm taking some random values like this, and I'm asking to generate text corresponding to that random values. Like this, it is generated. Or if you give input and it will generate corresponding output, reconstruction output. Don't worry, that is wrong, because if you run on the huge data and a huge number of epochs, it will give the reconstruction text, or we can say reconstruction characters or words similar to the input, So this is the way. Two things we can do by using variational encoder. One is reconstruction we can do. Another is generation we can do. So here, as per the instructions from the coordinators, I'm giving some break. Quickly, I'll come back within 10 to 12 minutes. All of you be ready, because I didn't take even lunch also. Quickly, I'll take water and come back. I'll take some snacks. All of you, please take a break. Thank you. I hope all are back now. Yes, that code. Sorry, I'm going little fast in the code also. Line by line, I can explain, but I can't do now because due to time constraint. So next one is GANs. We started GAN contains generator and discriminator. What is generator? Responsible for creating new data. See, GAN is like tug of war. We can say that word, right? It contains like that. One is generator, generates fake data, and it means it's create new data. Obviously, create new data means fake data only it will create. What discriminator will do, which is responsible for distinguish real and fake data, which will take both real input and generated input, and it will discriminate it. In generator, what is our target? Why these two models are there? Our target is we need to generate fake data. Okay, our target is we need to generate fake data. Then why discriminator we are keeping? The discriminator we are keeping so to guide the generator to generate the fake data as similar as original data, What generator will do? Generator tries to fool discriminator, and discriminator try to identify whether it is a fake data or original data. Both are important for us. So over a period, discriminator is unable to identify the fake data and original data. Up to that, we should train the GANs. Okay. Afterwards, so the generator will generate fake data as similar as original data. That is the overall theme. GANs were inspired from game theory. The generator and discriminator will compete each other to achieve Nash equilibrium. One thing is generator try to generate fake data, and try to fool the discriminator. The discriminator, what it will do, it will always try to identify the fake data or original data. So achieving the desired outcome, not by deviating from initial strategy during its training process. So what is the training process? All this we will see. Hello. అతమ నేను మళ్ళీ చేస్తా ఒక క్లాస్లో ఉన్నా. Yeah, the architecture you can see. The generated a fake 100 rupees note, and discriminator will take actual 100 rupees note and fake 100 rupees note. It will identify some features, right? Same way like image. You take image. Suppose some like Abdul Kamalam image, you take it, original image and a created image. Those discriminator will try to differentiate with, see, it will take both input at the time of training. We can train on both real and fake images. This is like a classification model. Okay. Fake or real. Okay. Fake or real, like 0 or 1. It will do like that. So first at the time of training, I'll talk about training, but discriminator, what it will do, it will take both a real image and fake image, and it will try to tell whether it is a fake image or real image. If you take the generated image, it should tell fake image. If you take this actual image, it should tell that actual image. Now, see what will happen. So the generator initially generated like this image and tell that this is a cat. What generator will do? Generator generated like this cat, a cat image. The discriminator told, so it is a fake. It is not cat. Next time, after so many iterations, the generator tried to generate this type of cat image. And discriminator said this is also not cat. Over a period, the generator, even more attempts later, generated will generate image like this. The discriminator said it's a cat. Even though it's a fake image, the discriminator is unable to identify whether it's a fake or original. Okay, fake or original. This is the way it will work. Both will work. Now, generator in GAN is a neural network that creates fake data to be trained on the discriminator. Okay, fake data. It learns to generate plausible data. The generated examples or instances become negative training examples for the discriminator. Obviously, positive, negative. Positive means actual data. Negative means this generated data. It takes a fixed length random vector carrying noise as input and generates a sample. Okay. How it will generate? It will generate from noise. It will take generator. You see, this is the generator. Again, it contains convolution neural network. Again, it contains convolution, or we can say deconvolution network. Okay. In one of the recent interview, the panel members asked this question: what a generator contains? Generator contains convolution network only. This we can say deconvolution. Convolution means from a huge to small convolved feature vector it will generate, but deconvolution means from small input to large output it will generate. So it will take some noise from after doing convolution, all these things, it will generate some big output. That is the fake image. What it contains, the dense layer contains, reshape, convolution transpose contains, batch normalization, leaky ReLU, all these things contains. If you are familiar with convolution neural network, this is easy to you to understand. The generator is deconvolution and pooling layered network image generation. So it will take small noise. So it will generate big image like this. See, it will take 7 by 7 image or noise and unpooling, and so on it will do. It will generate image like this. This is the task of generator. What generator contains? Deconvolution network. And discriminator. The discriminator is just a normal binary classifier. So it will take real image and fake image and it will classify. Both at a time it will not take actually. It will take either real image or fake image. If it takes real image, it should classify as 1. If it is a fake image, it should classify as 0. Again, which contains convolution only. Which contains convolution only. Okay. Next. Now you see working mechanism, random noise, generator, generated a fake image, training set, real images, all these fake images and real images send to discriminator, which will classify as real or fake, Actual mathematical background, what will happen? By saying it is very easy, but if you understand mathematically, it's very, very complex. Now, some noise we are taking. Okay, some noise we are taking. So we are giving to the generator. Okay, generator we are giving to the generator. So this is a generator. What we are generate from like a reconstructor. A generator, what it will do? It will reconstruction only, right? It will reconstruct data. That reconstruction data distribution, we should try to bring this distribution of the data has similar to the original data distribution. So meaning, what is the meaning of is whatever the noise we took from some sample from some distribution. So that noise will give to generator. Generator will generate some image. Those image distribution images distribution or data distribution. So we should try to bring this distribution in the form of same original data distribution. Then obviously what will happen? So this distribution, the generated images came into this original distribution. Obviously the discriminator is unable to identify whether it's a fake or original. Okay, please try to understand one more time. It will take some random noise. Okay, and it will generate some image. You take image here. That image distribution is, okay, that image distribution is different initially. The original data distribution is different. That's why discriminator will try to identify whether it is a original or fake. Over a period in the training, the generated image distribution is same as original data distribution. Then discriminator is unable to identify whether it is a fake image or original image. Fake image or original image. Yes. Okay. Now take this example. Okay, this example you will understand clearly. Okay, how can we build a generator and discriminator? So there is a slanted land. This example I took from some reference. I hope somewhere I give a reference. Simple GAN. There is a slanted land where people like walk like this in slanted people like this. Imagine there is a 2x2 screens. I can represent these images in these four values. In these four values, 2x2 screens. So now face only I'm representing in 2x2 image format. So this is the slanted face. This is a slanted face. Slanted face means the diagonal values are more, anti-diagonal values are less. Okay, just imagine like that. Okay, so our slanted diagonal values, some values are there. These are no values. So this is also face, but little slightly another diagonal values also there. This is another face, actual face, slanted face. Diagonal values are more. This one is not. Now take this, like this we can represent. The faces are converting in the form of numbers. Okay, these are no faces. These are faces, but with some noise also there. These are non-faces because anti-diagonal values are more. So like this, these are no faces. No face. Faces means values looks like this. Diagonal values some like diagonal values are more, like opposite diagonal values are less. No face means random values. No faces means random values. For this, how to build generator and discriminator we will see. Okay. Don't think what is this nonsense of faces, slant faces, nothing is there. But for our understanding, we took that example. This is the best example what I saw. So that's why I took this example. Simple GAN building the discriminator. Okay, what we are doing, we are building the discriminator. Okay, so to identify whether that image is converted in the numerical format. From that numerical format, we need to identify whether that is a face or non-face. How discriminator will identify. So now you see faces means diagonal values are big, anti-diagonal values are small. So noise means any random values that we know. What we can do to identify discriminator, what it will do, add main diagonal values and subtract that from other diagonal values. Okay, so we will get high value for face and low value for noise. Correct? If diagonal values are more, suppose this is the face, so what they did, yeah, this one into we constructed a neural network discriminator. So you see, this is the face. Okay, this is the my discriminator. So it is taking this diagonal first value to this node, and this second value this node, third value this node, fourth value this node. We are passing, and each link labels are plus and minus. Main diagonal link weights are plus, anti-diagonal link weights are minus. What we are doing indirectly, we are adding these main diagonal values and subtracting the other diagonal values. We constructed the network like this. Assume bias is -1. Assume bias is -1. Now this you see 1 into +1, there is 1. This 0 into -1, 0. this 0 into -1, 0, 1 into +1, 1. So total value 2 I'll get, 2 minus bias 1. What I'll get? 1. This I'll send it to sigmoid function. I just told the sigmoid function like this. Sigmoid of that value is equal to 1 by 1 plus e power minus x. Means the value always comes between 0 to 1. So 0.73 I got it, which is greater than or equal to 0.5. So I'll assume as 1. 1 means this is a face. Like this it will identify. See how like beauty with this deep learning neural networks is converting the image in the form of numbers. And by using those numbers, we are playing and we are identifying. So non-face, you take this example. 0.25 into 1 plus 1 into -1 plus 0.5 into -1 plus 0.75 into +1. So bias -1. Total, I'll get minus 0.5. The value I'll get 0.37. Whether it is a positive or negative, sigmoid gives between 0 to 1 only. If it is negative, small values it will get. If it is positive, if it is this value is below minus 0.5, small value will get. With it, if it is above positive value, big value, it will give close to 1. Okay. Now 0.37, which is less than 0.5, I'll assume as non-face. Now in this way, discriminator identify whether it is a face or non-face, or it is a face image, non-face image. For suppose my generator generated a face image like this. These numbers it generated like this. From the discriminator will identify it's a face image or non-face image like this. Okay, this is the way we can build a discriminator. Now generator, how it will generate? Okay, so now what I'm taking between 0 to 1, some random number I'm generating. Some random number I'm generating. That random number you take now is 0.7. So 0.7 I given. So this single input it is taking. Means generator what it will do, small input it will take, it will generate big output. Okay, big output. Some biases I took like this. So now I build the network like this, and finally I generated a image like this generated. This is if you give this one to the discriminator, it will say it is a face image because we will get good value. Okay, we will get good value. Like this, we can build the generator. We will build the generator. So how this generator, why we decided these values are like this? At the training process, these values are adjusted. I know now I given these values, but actually these values are adjusted at the time of training, generator and discriminator model training, GAN training. Okay. Here also these values are fixed, like weights are assigned at the time of training. Okay, that we will see. Now GAN working on MNEST dataset, handwritten digits. So this is the ground truth. Epoch 10, generator generating like this. Epoch 100 generator generating like this. So now see, if you see after 10th epoch, we can't identify that like handwritten digits properly. After 100th epoch, and after 100th epoch, we got somewhat like visible handwritten digits. So we can train any type of, like we can generate any type of data by using GANs. Now training, see, we understood how to build generator, how to build a discriminator, but how to train the generator and discriminator, the GAN training, we should understand thoroughly. Otherwise, it's difficult to understand. Okay. GAN training, start GAN training in alternative periods. Means one time I'll keep generator ideal, means please understand very clearly. Generator ideal means these values I'll not update. These values I'll not update. Randomly some values are given. I will not update those values. So that is the meaning of that the discriminator trains. Okay, alternative periods means once I keep generator ideal, I'll train discriminator. Another time, alternatively, another time I'll keep discriminator ideal. I'll update generator values like this. The discriminator trains for one or more epochs, then generator turn. These steps repeats. Means it's like maybe in the operating system, you know this round robin scheduling algorithm. After every time, it will give chance to other process. Similar way, here two processes are there. One is discriminator, another is generator. Generator I'll train for few epochs, then I'll train discriminator. Because why I'll not do only one time generator, I'll adjust and then discriminator? No, it is not work out. Once generator will parallelly, I need to strengthen generator and discriminator also. Discriminator after 10 epochs, discriminator is trying to discriminate fake and real properly. Then after 10 epochs, generator will generate very good fake image that a discriminator may not be able to identify like this. And so what we can do, generator, we will train some epochs by keeping discriminator ideal. Discriminator, I can train some epochs by keeping generator ideal. Careful training is required as most challenges of GANs are in training phase only. Yes. How many epochs we have to run? So this is very challenging actually over a period. So 10 epochs generator, 10 epochs discriminator. Then we can repeat this cycle multiple times. Maybe sometimes we can generator, we will do only 5 epochs, and discriminator we will do 10 epochs like that. Okay. So optimal training duration will depend on complexity of the data being generated, size of the training data set, and desired quality of the generated data. So how many, when we can stop it? Most of the classification models, when we can stop it? So based on the loss or based on the back propagation, weights are not updating. Various terminating steps are there. Here also, these are the terminating steps. If more complex data, if you want to generate, you need to train more number of epochs and so on. Stopping the training. When to stop the training? Generator is able to produce high quality samples that are identical to real data, then we will stop it. Our discriminator is no longer able to classify real fake data with high accuracy. Okay, it is not classifying. It is doing like discriminator is doing nonsense. Like a discriminator accuracy is too poor. Meaning is, see, sometimes the discriminator is very poor means it is good only. We are generating good images. We are generating good data. Okay. So in two cases, we can terminate the training process or we can stop the training process. Yes. Now see, generator training. Okay. Generator training, what we can do, generator training, only generated network weights only we can update it. That time discriminator keep ideal. Okay, discriminator keep ideal. The discriminator kept constant during the generator training phase, else the generator would try to hit a target and never converge. Okay, never converge. So that's why we can keep ideal. So first randomize will give generator output and discriminator classification and loss calculation from the discriminator classification. This last one we will do. Back propagates through both discriminator and generator to obtain gradients. Use gradients to change only generated weights. Here only we can change it. Here we will not change it. Now you see discriminator training. During the discriminator training, the generator is passed. Passed means generator will not update, only generates continuously, which will take real data and fake data and it will try to identify. Okay, fake image it will take it. Discriminator classification, loss calculation, back propagation, use gradients to change discriminator weights. Okay, gradients means gradient descent optimization techniques are there. Add model delta, SGD. By using that, we can update this discriminator where like parameters. Okay, parameters. So meaning is when we are training discriminator, the generator parameters will not change. Generator parameters will not change. So back propagation in discriminator training. So only in discriminator we can do back propagation. Now GAN's loss function. Okay, this is a little complex loss function. So what it's a min-max loss, we can say min-max loss. What generator will do, generator, please listen this sentence, generator tries to increase the loss, meaning is generator tries to fool the discriminator. When discriminator is weak, so obviously the loss becomes, it is unable to identify fake and real properly. And come to discriminator. Discriminator tries to minimize the loss. Okay, that's why we can say, okay, min max. Okay, so min max we can, discriminator predicts on fake data. This is the discriminator predicts on real data. This is the mathematical formulation. The standard gas loss function, also known as min max loss. The standard GAN loss function is divided into discriminator loss and generator loss. Okay, so these are corresponding things. Okay, corresponding terms. So please remember, generator tries to increase the discriminator loss, but the discriminator tries to reduce the discriminator loss. Okay, yeah, it works like that. Now for discriminator, yeah, some mathematical functions are given. How discriminator value becomes 0, all these things. Minimizing, yeah. So please go through this one. Discriminator loss and generator loss, both we can combine. Yeah. This loss, you please go through it. GAN challenges. What are the challenges in GAN? Okay. Mode collapse is one of the biggest challenge in loss. To overcome this, there are various techniques nowadays. Mode collapse means generator generates very good fake data, which is very similar to input, but it is repeatedly generated same thing. Imagine, repeatedly generated the same thing. Okay, then it is useless, right? Whatever the generated, like suppose I'm generating different people images, but every time it is generating particular person image only. That is useless, right? That is mode collapse. GAN fails to capture and generate diverse samples from the entire data distribution. Only particular data distribution it is generating image. So GAN should generate very good fake images, diverse images it should generate. Instead, it focus on generating samples from only a few modes or patterns in the data. This results in lack of diversity in the generated outputs. Why it is a challenge? It makes the generated data less useful for the task like data augmentation. And why we are trying to generate fake data? That is another important. We generate fake data for augmentation purpose. Data augmentation, some critical scenarios, more data set is required. So suppose some satellite images, you take it. Some forest related images, you take it. We have very less images. Okay, but we need more images. By using generator, we try to generate more images. So it should generate diverse images. Otherwise, what it will become? It will become that for like a synthesis, like it is not data augmentation. For data augmentation, it becomes useless. And creative content will not generate. Creative content it will not generate. So this is the problem with the GANs, mode collapse. Non-convergence issue is the discriminator performance get worse when generator outperforms it. Okay. Sometimes what happens? Generator is generating very good. Okay, discriminator becomes nonsense. Okay, this is also not good. So always we try to generate good image, but a discriminator should also work very good. Otherwise, what will happen? Then accuracy of the discriminator becomes worst. Okay, lowering the accuracy of the discriminator. Why it is challenging? The discriminator feedback get less meaningful over the time. So discriminator feedback is very important, and generator should generate very good like data also. Gives random feedback to the generator by which the generator starts to train on junk feedback, reducing its own quality. Suppose I'm trying to generate dog images. Okay, I have very less dog images. I have cat images. Like I have few dog images, original dog images. I am trying to generate dog images. Discriminator is not performing well. Due to that, over a period, the generator generates cat images also. Generator generates cat images also. So it's like that. This is non-convergence. Now, coming to the applications of generative neural networks. So, like, what are the application? Image generation, image to image translation. So, translation, I shown one image, okay, initially, before one photographer translated to original image. You see, it works like this. Now, general classification, it will do super resolution, it will do semantic segmentation, conditional image resolution, classification, image super resolution, face generation, all those things it will do. So this is the example. Before going to LLM, how can we generate images? We will see few examples. So then I will load notebook. Image generation, I will see show. So this is loading libraries, NumPy, TensorFlow, import Keras, we can import Keras, and the layers we can import it. So what data set we are taking? MNest data set only, handwritten digit data set only. Okay. So which is there in Keras data sets. Directly we can import it. Okay. See, we are importing those, only we are taking training images, not the corresponding class labels, only training images I'm taking. Okay, what extrain, xtest. Okay, we are taking extrain, xtest, extrain, xtest. We are taking extrain means only training, for training some sample. I'll take it corresponding class label. Xtest some samples I'll take for testing. So now you see total these many emojis are there. Done. Latent dimension 2-dimensional. We are doing with a variational autoencoder only. So now encoder network, this convolution 2D network, flat and dense layer we are doing. This is a mean sampling we are taking. Encoder model. Encoder model convolution neural network summary, if you see like this. Encoder model 28 image it is taking, converting to 14 by 14, 32 images, and then converting to 7 by 4, 64 images, and flattened converted these images into 3136 one-dimensional vector, and 16 neurons it is giving, and finally it will generate two values. Okay. Now you see this decoder network. Decoder network looks like two input it is taking and converting 3166, finally generating 28 by 28 image. Variational autoencoder model. This is the model and train it. Each epoch, if you see, if you observe each epoch, first epoch, 30 epochs I'm training. Oh, some error it is giving. Okay, so just wait. Then image generation, we will go for GANs. Just wait. Error, because we can correct it, but it will take some time. What I will do? Image generation. Generation using DC GAN. So this mount drive means when data is there in your drive, that time we can use it. So training time, this model, you see how it will train over a period. We'll see that. TensorFlow version, pip install GIFs required that to represent the generated output in the form of image. We use this, and GitHub's related things are there. And these are the packages. Next, same MNeST data set only. We are taking train images, train labels. We are taking. This is for GANs. Okay, class labels also required. Original samples also required, right? Train samples, buffer size, train data set. Because given downloaded data set of the images, randomly it will shuffle it, and it will take some train set. Okay. So how many batch size? 256 batches. Total buffer size 60,000 images. Total 70,000 images are there. Out of that 60,000 images it is taking for train. So now this is the generator model. So generator contains, if you see, like 7 into 7 into 256, like converted into, this is a single value. From this, it is converting this many vectors or two-dimensional matrices and so on. Finally, it will generate 28 by 28 image. This is the generator task. So generator, it will take randomly a random normal. So it took random normal 1 to 100. Some values it took. So it is generated like this image. Okay. So the discriminator, you see. So this is the discriminator model. Okay. So now define loss, cross entropy loss, discriminator loss, the generator loss, generator optimizer, save points, checkpoints we can keep because it will take a lot of time. We can save after few checkpoints. Epochs 5, noise dimension 100, number of samples to generate 16. Now you see. Generate. Now training. You see training. Sixteen images we are generating in every epoch. Okay. So how it look like, you see. Yes, this how it generated 16. Okay, 4 into like this 4 into 4. Now, see what time for first epoch, this much time it took, it is generated like this images. Next, second epoch, it is generated like this. See images, how it is transforming slowly. Third epoch, it is generated like this. Okay, so like this over a period, it will generate. I think it is still running. 5 epochs we did, right? Taking time. Yeah, fourth epoch, if you see, little bit good shapes are coming for handwritten digits. Previously, if you see this, will not understand anything. Next, if you see this, will not understand anything. You see this, still we didn't understand anything. From this, at least we can guess something. This is 1, this is maybe 1 or 4, this is maybe 5 or 0, something we can guess it. In fourth epoch, some more shapes came like this. So done. 5 epochs done like this. Okay. If you run for 100 epochs, the generator will slowly generate good images. Okay, handwritten digits. Now, yeah, output that final after epoch. This is the image. If you see this, at least its shapes are like 7, 3, 2, like this. We can see, we can observe. Now, the training, the okay, animation in animation they shown here. This images. If you run this, see, after some epochs, finally it is generated like this. If you run for 100 epochs or 200 epochs or 500 epochs, which will generate very well. which will generate very well. So what you have to do, actually, this is actually 5 to 6 hours sessions. We are doing very fast. So line by line, I will explain line by line everywhere, but due to time constraint, I'm not doing that. Now quickly, so after GAN, finally, I'll get this type of image. Okay, best image. Now next, large language models. What are large language models? So I will quickly go through some theory points. Large language models in introduction. Large language models are deep neural networks only. Okay, but what happened? Pre-trained models. Okay, these are pre-trained models trained on massive text corpora to understand, generate, summarize, translate, and reason over human language. Okay, maybe nowadays it is generating text, it is generating image, all those things it is generating large language models. If you give some, like what we can say, prompt, according to the prompt, how best you will give prompt, accordingly it will generate the text or image, whatever it is. So large language models means it's the deep learning models only, pre-trained models, because in deep learning we discuss about different pre-training models like ResNet, GoogleNet for images, and so many VGG16, VGG19, so many pre-trained models are there. Like that, these large language models also deep learning models. Those are not special, but these large language models are trained on massive data. Somebody is unmuted, please mute it. Or somebody is trying to ask me something. Now, what is the use of these large language models? It text corpora to understand, generate, summarize, translate, and reason over human language. LLMs learn statistical patterns, semantic relationships, and contextual dependencies through self-supervised learning. Okay. So it will not simply understand the distribution, not only understand the pattern, not only understand the relationship in words, all those things, and contextual context based on context. All these it will understand through self-supervised learning techniques. Key characteristics of LLMs are billions of parameters, large context windows, transfer learning, emergent capabilities. Okay, so these are the characteristics of LLMs. Popular examples we know ChatGPT, Gemini, all these things we are using. Applications where we can use everywhere. Nowadays, in the healthcare, it is very less. LLMs are not working that much great because still people are trying to build specialized racks, okay, for a specific domain, all those things. But yeah, uh, which are using in healthcare, education we are using left and right, and especially in academics we are using to generate programs, all those things. In industry also we are like industry also they are using this program generation, and even in testing also for workflows, everything they are using. Scientific research, software development, and business automation, everywhere we are using this LLMs. Now, foundations of LLMs. LLMs, so here in LLM means tokenization converts, tokenization means splitting the input into smaller units, smaller tokens. If it is like a text data converting into words, if it is an image converting into small images that can be processed by neural networks. Okay. So embedding transform tokens into dense numerical vectors representing semantic meaning. So see, tokenization is there and embedding is there, and pre-training uses next to token prediction on large dataset collected from books, websites, articles, and code repositories. So like that they train. Fine-tuning, like after training, fine-tuning we can do for specific tasks. Okay, suppose few images are there or few text is there for specific task, we can fine-tune the model, that pre-trained models for specific domains such as medicine, law, bioinformatics, finance, whatever you want. So initially the pre-trained models are So ChatGPT is a pre-trained model. If you give some text prompt, accordingly it will generate some text. Okay, so it will generate some text. Please understand that generated text should be within the same distribution of the input, trained input. Okay, so in that way it will generate it. Evaluation metrics including perplexity, accuracy, and so on. We use specific task-specific benchmarks are there, how well that LLM is performing. Okay, now transformer architecture, what it contains, transformer architecture it contains. Okay, transformers replaced current architectures by enabling parallel processing of entire sequences. Okay, transformers parallelly process the entire sequence without missing the context and without missing the dependency and without missing the, what we can say, order. Okay, sequence order also. So core components include in the LLMs what it contains, which include token embedding, just embedding, the conversion of into tokens and embedding, positional encoding. Okay, positional encoding means so randomly it will process the tokens like parallelly. The position of the sequence also important. That's why positional encoding is important. Self-attention, which will focus which part is more important. Multi-head attention and feed-forward neural network, residual connections, and layer normalization. See, all these terms in deep learning we study. We should know all these concepts we use in LLMs. Self-attention enables a model to identify relationship between words regardless of their distance in the sequence. Okay, self-attention means which will focus which words are important in the sequence. Multi-head attention capture different contextual relationships simultaneously. Okay, contextual relationships. So contextual context, based on context for one given input, based on context, it will generate the different types of output. Suppose the context is particular scenario, particular context it will generate. This that multi-head attention will take care. What are the advantages of this architecture is scalability, efficient training, long-range dependency modeling, and state-of-the-art performance it is giving. Advanced LLM architectures and techniques. Okay, so nowadays we are using RAGs, retrieval augmented generation, combines external knowledge retrieval with the language generation. Okay, some external knowledge at the time of generating text or image, some external knowledge also we are giving, accordingly it is generating RAG. I hope in further sessions this RAG is there, so they will discuss in detail. So now instruction tuning improves model alignment with the user intentions and the task requirements. That's where prompt engineering also nowadays playing crucial role. How best you will prompt, accordingly will get your required output. So now reinforcement learning from human feedback enhances helpfulness, safety, and the response quality. Obviously, reinforcement learning also giving reward for the generated text. If it is expected text, you will give positive reward through reinforcement learning. If your generated text is not positive, penalties you will give through reinforcement learning. In that way, we can fine tune the model or we can fine tune the model. Now, parameter efficient fine tuning methods such as LoRa reduce computational cost while maintaining performance. Emerging architecture support multi-model inputs, including text, images, video, audio, all these type of things it is generating. Next, what are the applications? Applications, healthcare, we are using bioinformatics, we are using protein sequence modeling, biomarker identification, molecular property prediction, all these things we are using in bioinformatics. Clinical decision support. Nowadays, we are also working on RAG for what we can say cancer therapy recommendation. Okay, healthcare like clinical decision support. So like medical report generation, drug discovery, genome analysis. In education, intelligent tutoring system, personalized learning, and automated content creation, all those things we are using. What are the challenges? Challenges include so many challenges like that it will assume something and it will generate text. Hallucinations are there, bias is there, privacy concerns are there, explainability problems are there, computational requirements also there. Huge computational requirements is required for LLMs. Next, future directions. So next, agentic AI. So after this, like scientific discovery assistant, trustworthy AI, domain specific foundation models. These are the future directions. So I hope that's it from my side. If you have any queries, yeah, before that, I will share this PPT, that code. Please explore again the application of this today's whatever the application we discussed. You use this application, ChatGPT application, to understand line by line. That is the best way. Previously, we usually search in Google, so many blogs we need to read. Now ChatGPT is solving our problems easily. That itself application. Okay, whatever the code we gone through, please go through that code. If you will not understand line by line, you please give to ChatGPT. It will explain you. So that's it. I hope I given lot of data and to you. So thank you very much.
Thank you, sir. Thank you, sir, for the highly informative and insightful session. The concepts and practical.
Any queries from participants?
No, sir.
So then shall we leave?
Okay.
Okay, then thank you very much. Thank you, participants, for your patience continuously from 2 hours, 35 minutes. So thank you very much. Thank you all.
Thank you, sir. The concepts and practical perspectives shared today on generative AI and LLMs are truly enlightening. We are grateful for your valuable time and expertise. On behalf of the organizing committee and all participants, I extend our sincere thanks to you. Thank you everyone for your active participation. We look forward to meeting you again in tomorrow's session. Have a pleasant day. Good day.